So welcome to the last unit in the topic of solids, liquids and gases, the concept of specific heat capacity. So it's going to be related to changes of state, and we're going to have to learn what the specific heat capacity is, why heating a system will change the energy stored in it, and use the equation delta Q equals mc delta T, which we'll learn about more as we continue on in the lesson. So here we have a hot apple pie in a paper container. Okay, so have you ever bitten into a hot apple pie and burnt the inside of your mouth? The outside is warm, but the inside is very, very hot. And it was all cooked together in the same oven, so why does this actually happen? Well, it's because the filling has a higher heat capacity than the pastry, and that's what we're going to be learning about today, heat capacity. So heat versus temperature. What is the difference? What I want you to do is watch the following video and write down the definitions for heat and temperature.
Temperature versus heat. Here's a bucket of hot water at 50 degrees Celsius. And here's a cup of freshly boiled water at 100 degrees Celsius. In which of these two containers are the water molecules moving faster? The bucket or the cup? That's right, because the degree of hotness of the water in the cup is much higher than the degree of hotness of the water in the bucket. And the hotter something is, the faster its molecules move. Would you say, therefore, that there's more hotness in the cup than in the bucket? In that case, if the water in your swimming pool is just a bit too cold for you, you'd be better off emptying the cup full of boiling water into it, rather than the bucket full of water at the lower temperature, wouldn't you? Or would you? You don't seem so sure. Let's do an experiment to find out. Suppose you had two identical swimming pools, one yellow and one blue. And suppose that the water in both of them was just a bit too cold for you. When you pour the cup of boiling water into the yellow pool, does the water feel any warmer? You can hardly feel any difference at all, can you? Now pour the bucketful of 50-degree water into the blue pool. How does that feel? Quite a bit warmer? Aha! So even though the water in the cup was considerably hotter than the water in the bucket, the 50-degree bucket water is much better at heating up swimming pools than the 100-degree cup water. Why is this? Well, let's look at the facts. The bucket obviously contains many, many more water molecules than the cup does. The temperature of the average molecule in the bucket is 50 degrees, and the temperature of the average molecule in the cup is 100 degrees. Now let's substitute something else for the molecules. Imagine that instead of molecules, the cup were filled with $100 bills, and the bucket with $50 bills. Which would you rather have? Each individual bill in the cup is worth much more than each individual bill in the bucket. But the total amount of money in the bucket is much greater than the total amount of money in the cup. It's the same with hotness. The degree of hotness, like the value of the dollar bills, is higher in the cup. But the quantity of hotness, like the quantity of dollar bills, is greater in the bucket. We've already seen that the word for degree of hotness is temperature. Now it's time to introduce the other word for quantity of hotness, which is heat. The water in the cup has got a high temperature, but very little heat. And the water in the bucket has got a much lower temperature, but a great deal of heat. Now you know why buckets of 50-degree water are better at heating up swimming pools than cups of boiling water. On the other hand, if you're looking for somewhere to dunk your tea bag...
So heat is the thermal energy contained in an object, whereas temperature is the measure of how hot something is. So the gas particles on the right of this diagram have more kinetic energy than those on the left. So that would mean that the gas on the right has a higher temperature because it's going to have more kinetic energy. Whereas heat is the thermal energy contained in an object, not the kinetic energy. When heat energy is transferred to an object, the temperature will increase because, as the diagram shows, when you transfer heat energy into an object, that heat energy is then converted into kinetic energy, which is a measure of temperature, or how hot something is.
Here are two identical pans. One pan contains 200 grams of water, the other 400 grams. Everything is at room temperature. The pans are placed over identical gas hobs. Which pan of water will boil first? Obviously the one with less water. The pan with more water needs more energy for its temperature to change by a given amount. Its heat capacity is higher. So heat capacity depends on mass, but does it also depend on the substance being heated? Compare the heat capacity of cooking oil with water. Each pan contains 200 grams. Water on the left, oil on the right. As the pans are heated, the oil temperature increases rapidly. When the water starts boiling at 100 degrees Celsius, the oil temperature has reached over 130 degrees. For a given temperature rise, the oil needs less heat energy than water. We say that oil has a lower specific heat capacity than water. The specific heat capacity of a substance is given by the heat equation. Q is heat energy added to the substance. M is the mass of the substance. C, its specific heat capacity. T1, the initial temperature. T2, the final temperature. So T2 minus T1 is the change in temperature. Rearrange this equation to make C the subject. For example, let's find the specific heat capacity of aluminium. This cylinder is a 1 kilogram block of aluminium. Place an electric immersion heater in one hole and a thermometer in the other hole. Note the initial temperature T1, 27 degrees Celsius. Connect the heater to an electricity supply and switch on. After 20 minutes, switch off and note the highest temperature reached, T2, 37 degrees Celsius. We know the mass M equals 1 kilogram. And from our experiment, the temperature difference is 37 minus 27 equals 10 degrees. So these figures complete the bottom line. Now the energy added, Q. Assuming that all the heat supplied by the heater is received by the aluminium, Q equals VIT, where V is the voltage of the immersion heater, 5 volts, I is the current, 1.85 amps, and T is the time the heater was on. 20 minutes equals 1200 seconds. So multiplying these together gives Q equals 11,100 joules. Finally, substitute this value into the heat equation, and our calculated specific heat capacity is 1,110. The units are joules per kilogram per degree Celsius. The actual value for the specific heat capacity of aluminium is 908. So our experimental value was quite close. Can you suggest causes of error and improvements to our experiment?
So from the video you've just seen, what is specific heat capacity? So if we consider 3 different substances, copper wire, a limestone rock, and a cup of water, specific heat capacity is a measure of how much energy each material can store. It is the energy needed to raise the temperature of 1 kilogram of a material by 1 degree Celsius, and its units are joules per kilogram degrees Celsius. So if we heated the 3 materials below for 10 minutes, which one do you think would get the hottest? So in terms of specific heat capacity of different materials, of the copper wire, the limestone rock, and the cup of water, if you heated the copper wire for 10 minutes, it would get a temperature of 82 degrees Celsius. The limestone would have a temperature of 65 degrees Celsius, and the water would have a temperature of 43 degrees Celsius. So from these numbers, you can determine roughly what the specific heat capacities are. The copper became hottest because it has the lowest specific heat capacity. It doesn't take as much heat energy for the copper to change 1 degree Celsius in temperature. Whereas limestone is kind of in the middle, and water has the highest. Okay, it absorbs the most heat energy without becoming very hot, without having that large increase in temperature, which you see with copper. Okay, so different materials have different specific heat capacities. Okay, so water has a very high specific heat capacity of 4,200 joules per kilogram degrees Celsius, which means it takes 4,200 joules to increase a kilogram of water by 1 degree Celsius. Whereas copper has a low specific heat capacity, which means it doesn't take as much energy, 390 joules, to increase a kilogram of copper by 1 degree Celsius. So which of these would get the hottest? 1 kilogram of glass or 1 kilogram of iron? I would say it's going to be the iron compared to the glass, because it has a lower specific heat capacity, which means it doesn't require as much heat energy to increase a kilogram of iron by 1 degree Celsius. In fact, about half as much as glass. Which of these materials is used in heat radiators? That would be oil, okay, and the reason why is it's actually storing a lot of heat energy, and it doesn't increase in temperature as much, because obviously if it increases in temperature, oil will blow into flames. Okay, we don't want that. So we want a kind of a reasonably high specific heat capacity. What other materials could be used in heaters? Okay, I guess you could use, again, water, because that would again mean that lots of energy is required, and of heat energy is required for that temperature rise. So you get that slow release of heat energy. And which would feel colder after 1 hour in the fridge, limestone or copper? Again, that would probably be the, good question, that one. So which one would feel colder after 1 hour? It would probably be the copper, because it's going to release the heat energy a lot faster than the limestone. So the equation for specific heat capacity is calculated using the equation Q equals mc delta T, where Q is the heat energy transferred in joules because it's an energy, m is the mass of a substance in the units of kilograms, and delta T is the temperature change in degrees Celsius, or, well, that's the symbol degrees Celsius. And C is the specific heat capacity in joules per kilogram per degree Celsius, which is unique for the particular substance that you are heating. So you can also rearrange the equation. The mass can be equal to Q divided by C times delta T. The temperature change, delta T, can be equal to Q divided by C times M. And finally, the specific heat capacity can be Q divided by C times the change in temperature, delta T. So let's look at the frying of an egg in paper. Okay, so can you fry an egg in newspaper? So think about that. Watch the video, but while you're watching the video, can you actually explain how it works? In fact, what I'd like you to do is try and work out, can you explain how it works first, and then watch the video. So let's have a look.
The question is, how on earth do you fry an egg over a stove if you haven't got a frying pan? No, I'm not entirely sure what we do with that. Maybe leave it for a little bit and see what happens. Oh! Yeah, that's not too bad. Would you eat it?
Not too sure about that.
Do you want me to show you a different way of doing it?
Yeah, go on then.
Okay, so you can do it with paper. Oh! I'll show you.
I've got a daily mirror here if you want.
Yeah, go on, mate. Yeah. I'll do it with a mirror. Do you want to?
I want to see this, man.
You think you'll just burst into flame, right?
Yeah.
Just in case,
Okay.
isn't it?
Burning, it's just a chemical reaction, and it takes a certain amount of heat to get the reaction going. That's because it takes energy to break apart long molecules like those in paper. In fact, it takes quite a lot of heat energy to make paper spontaneously burst into flame. Its ignition temperature, as it's called, is about 232 degrees centigrade. That's Fahrenheit 451. So if I just put some oil in, yeah, and treat this like a frying pan, like you would let any other normal frying pan, put an egg in it. So do you think it's going to burst into flame?
I thought the paper would go boom. I trained as a chef 20 years
Right,
ago.
okay,
That's
they
the
didn't
first time
teach
I've
you
ever
like
seen
this.
Bubbling. Oh, look at that.
It's cooking?
Yeah, bubbling. Yeah.
Yeah, it's frying, look. Yeah, it's cooking. Yeah, it's cooking.
Perfect.
Well, the egg is absorbing the heat and keeping the paper below that critical ignition temperature, but still quite hot, enough to fry the egg. That's probably done that. Looking all right to me. Shall I give it a try?
Yeah.
That's
That's amazing how that's done that.
Oh, you're clever, you are.
I'm quite hungry actually because I haven't had any lunch yet. So
That's not edible. I wouldn't.
really nice. Okay. Yeah,
That was delicious, actually.
fun.
I'm not going to give that a go.
So here are just a few questions that you can work on in your own time. What the specific heat capacity of 390 joules per kilogram per degree Celsius would be. Calculate the energy transferred when 3 kilograms of copper is heated from 20 to 220 degrees Celsius. Calculate the energy needed to heat 2 kilograms of water from 10 degrees Celsius to 9 degrees Celsius with the specific heat capacity of water given. And also, finally, suggest why more energy than you calculated in part A is actually needed. Okay, so pause the video now and see if you can get the correct answers there. Okay, so welcome back. So what does this mean, this 390 kilograms, joules per kilogram degree Celsius? Well, it means essentially that it takes 390 joules of heat energy to increase a kilogram of, what is it, copper by 1 degrees Celsius. That's what the specific heat capacity means in that particular example. Okay, so 1b, calculate the energy transferred when 3 kilograms of copper is heated from 20 to 220 degrees Celsius. Okay, so it's the heat energy transferred. So the equation will be the Q. So the equation will be Q equals mc delta T. So let's plug in the numbers. So the mass is going to be 3 times that by the particular heat capacity of, well, given it 390, okay, of copper, and times the temperature difference, which is 200. So you should have got, if I use my calculator, 3 times 390 times 200, which will be quite a lot, about 23,000, no, 234,000 joules, or 234 kilojoules. Quite a lot of energy. Right, calculate the energy needed to heat 2 kilograms of water from 10 to 90 degrees Celsius with the specific heat capacity of 4,200 joules per kilogram for degrees Celsius for water. Okay, so again, using this equation here, we're now just plugging in the numbers. So the mass is 2. The specific heat capacity is now a lot larger, it's 4,200. And the change in temperature is 80 degrees Celsius. So it will be 2 times 4,200 times 80, which will be, again, massive, 627 kilojoules. Okay, so comparing 1b with 2a, you can see the massive effect of this very large heat capacity of water. Okay, so similar masses of water and copper, but a lot more energy required to do the heating. Suggest why more energy than you calculated in part A is actually needed. Yep, because a lot of heat would be lost. Okay, so heat would be lost to the surroundings. Okay, so basically the heat transfer would also be lost to surroundings. Okay, because you're not just heating the water, you're probably going to be heating the container it's in. You're going to be heating the air molecules that are around the container. So a bit of heat would be lost in terms of the surroundings, so you have to use a little bit more than you would expect. So again, some more questions. 3II, 3II, and 3II, and 3IB. Okay. So here are the specific heat capacity values for 4 different metals. Okay, so let's see if you can work through these particular problems by yourself, and then come back if you think you've got the answer and see if you're right. Right, so welcome back. How much energy must be transferred into 1 kilogram of copper to raise its temperature by 1 degree Celsius? That's an easy one because you just use the specific heat capacity there. It'd be 390 joules. Suppose you have 1 kilogram of each metal. Which one will need the most energy to raise the temperature by 1 degree Celsius? That will be the one with the largest specific heat capacity, so that would be aluminium. The same amount of energy is transferred into 1 kilogram of each metal. Which one has the largest rise in temperature? That would be the one with the lowest specific heat capacity, which would be this alloy here, brass, which would just be slightly hotter than copper. And how much energy must be transferred into 2 kilograms of iron to raise its temperature by 5 degrees Celsius? Okay, so again, we're using the equations that we've already looked at. Q equals M times C times delta T. Okay, delta T, of course, will be the 5 degrees. So that will then be the mass, so it's 2 times C, which we will get from the table here. Okay, so 460 times 5, because that's the temperature raised, delta T. So it'll be 2 times 460 times 5, which will equal, not much really, 4,600 joules. Okay. Hopefully you got them all correct. So now I want you to copy and complete the following table, and remember to show all your working, and then we'll go through it together to see if you're on the right track. Right, so welcome back. So let's look at the materials A, B, C, D, E, and F and work out their missing variables. Okay, so the first one would be Q equals MCT, so it'll be just 4 times 6 times 4,000, which will be 96,000 joules. The next one, we want to know the temperature rise, so it'll be Q divided by C times M. So first we'll work out C times M, so 2,000 times 1, so it'll be 6,000 divided by 2,000, that's 3 degrees Celsius. Next one, we want to work out the mass. Okay, so it'll be Q divided by C times delta T, so it'll be 1,000 times 4, 8,000 divided by 4,000 should be 2 kilograms. Next one will be the QMCT equation, so it'll be 12 times 24 times 500, so 144,000 joules. Quite large, but we have quite a lot of mass, 12 kilograms. Now we're working out the specific heat capacity, which will be Q divided by M times delta T, so 2 times 5 is 10. So yeah, M times delta T, so so it's 10, 2,500 divided by 10, okay, which is going to be 250 joules per kilogram degrees Celsius. Make that more than a 5, okay, well that's very messy. Let's make that a little bit neater, 250, there we go. And the final one is going to be 0.75 times 15, which is 11.25, 1,400 divided by 11.25, which will be, strange number, but anyway, 124.4 joules per kilogram per degrees Celsius. Sorry, 124.4 joules per kilogram degrees Celsius. Okay, just double check that. It seems like a strange number. Yep, so mass times delta T, yep, that's right. Okay, so hopefully you got those all correct. So another example here, using the equation, how much energy must be transferred to raise temperature of 2 kilograms by 20 degrees to 30 degrees. And how much energy is needed to raise temperature of 1 kilogram of glass from 30 to 45 degrees. And finally, how much energy is needed to increase temperature by 500 grams of lead from 20 degrees Celsius to 45 degrees Celsius, giving the specific heat capacity of lead as such. It's up for you to work out. Okay, I'm not going to go as examples. They're just examples to further practice your techniques. And the final examples there with the summary questions, I'll leave those for you to complete in your own time. The key points from a lesson are: the greater the mass of the object, the more slowly its temperature increases when heated. The rate of temperature change of a substance when it's heated depends on the energy supplied to it, its mass, and its specific heat capacity. And storage heaters use off-peak electricity to store energy in special bricks. And that's pretty much all you need for specific heat capacity.